All right. Hello, my name is Ibrahim Mominov. I'm a master's degree student in the Department of Computer Science and AI, and I'm also a machine learning lab member under Professor Kim Ji-hee's supervision. All right, today's paper would be pretty much about an object detection. Not only, we'll also talk about how to integrate object detection with other models, which we call them multimodal large language models, where a model not only gonna see the text, but also sees the world based on what it sees, it makes the predictions and decision. So the paper is called Towards More Reliable Object Detection in Multimodal Large Language Models. And then this specific paper was published at CVPR and then in June 2025. So the authors are Dongguk University and YouTube Lab, a Tencent company. So let's go ahead and talk about this paper a little more and then see how they just integrate. All right, so before I get started, there is it would be better if we just talk about what exactly an MLLM is. So as we know, it stands for Multimodal Large Language Model, and then the key idea is pretty simple. Instead of only understanding the text like a normal LLM does, these models can understand both text and image together. So you can think of LLMs that grow a pair of eyes. So basically the little advanced options of the LLM. So they can read, they can look, and they can reason about the both at the same time. Because of that, they can handle tasks like describing what's in the picture, answer questions about an image, and even doing an object detections, which we exactly will be talking about in today's PPT. So overall, MML is as a bridge between computer vision and language understanding, letting us interact with images using human, natural language, and also using an everyday language. So so here's the core issue we're dealing with current MLMs. They work pretty good when you ask them to find a single object, but they fall apart when the descriptions involves multiple targets or something that is not actually in the image. So instead of saying nothing matches, they often guess, which makes their prediction unreliable. So we basically, LLMs, they don't really like to say no. Instead, they just rely on some kind of data. So that makes the object detection model to predict some wrong data or just rely on something called misclassifications. Even those kind of pretty advanced models like GPT-4 or here we have a Gemini, they also do some kind of mismatch a lot. So basically, they struggle with free-form natural language. So real descriptions involve actions, relationships, and negatives. And today's models handle that correctly only part of the time. So it's not just a technical inconvenience. I think it's pretty much incorrect visual associations can lead to serious problems, from mistakes in autonomous driving cars to make some errors, or maybe different AIs somewhere in healthcare. So on the right side, we can see some digits. So that basically where and how much models they just make mistakes. So of course, we have some related work. This is not only the work. So MLMs that try to improve object localizations, but they also share a similar limitations. So models like Shakra, and then also Ferret and Focus, they just pretty much focus on referring and grounding tasks, basically finding object that definitely exists in the picture already. And then pink, here we have another model. It pushed reasoning about a little bit further. And then Mini GPT tries to unify multiple localization tasks. So basically, these are the this topic across all of these models, pretty clear. So they all concatenate on grounding objects that are already present. So they're not built to handle multiple objects, free-form descriptions, or case where the object doesn't exist at all in the picture. So basically, all that gap is exactly where this current model will cover. So language-based, this is another part, but it's pretty much little. So those traditional detections limited to fixed categories like YOLO, right? So they're just pretty much on that cat, dog, or car, any limited data. But in fact, in real life, people don't talk that way. We describe the things in a full sentence with attributes and actions. So we basically, just instead of calling it that dog, if we just pass the text a furry animal, in that case, basically the model cracks. So another limitation is about the So basically about the language, which is the BERT. So it doesn't really, so basically BERT was trained on a massive data set. It's about like 33 million. But if we just ask the input, like a lot of kind of like ambiguous or just maybe calling objects by their functionality, in that case, BERT definitely cracks exist. So in order to solve this problem, and then the researchers came out with this key idea. So it split the problem into two different categories or two different parts. One part that's a great at finding possible objects, and the other word, it's pretty much great at understanding the language. So basically, model now understands the image first and also understands our prompt. So basically, based on the understanding both text and an image, they just bridge this gap. So first, the low-level component is an open vocabulary detection. So its job is simple. So it proposes all those regions in the image that might fit the user's descriptions. So then the high-level component, the LLM, steps in. It uses reasoning to decide which of those candidates regions actually match the full meaning of the text. So here's how the whole system works. The detector finds possible objects, and then it extracts local features, and those features get projected to the LLM's language space. In that case, the LLM then considers three things together: the global image, the regional feature, and then the user's text piece. Basically, entire what's happening in the image, and also the specific bounding box, what exactly inside an image might be. So in that case, the LLM has three different parts to understand. First, the user's text, and then whole image, and inside the bounding box. Another part that the researchers made it's like a major challenge in language-based object detection is the lack of training data, right? So to solve this, the authors built an automated data set construction pipeline. So using a chain of thought techniques, the system generates rich, diverse object descriptions and pairs with the image regions. So this allows the model to learn from a far more complex language than traditional data set provided. So the result is the ROD dataset, which contains over 500,000 descriptions image. And what really sets it apart, it covers coverage. It includes description that match multiple objects and also single object and even zero objects. So that way the model can understand to tell like, here's an object or all right, so this is the main architecture of their model. So as we see, we have both image and a text. And here we have a low-level locator. So this part receives the image, the query object, like a horseman and helmet. So as we see on the right side, we have a text to locate horseman's helmet or without the helmet. So this data and then the specific text will be passed into the low-level locator right here, as well as a picture. And then a set of common objects like person, bicycle, horse, everything. So what OVD does, it searches the image for everything and anything like that resembles like these categories. For example, if the words are like horseman helmet, the OVD might output a box of containing the rider horse helmet. So basically we have the full features extraction from the image and also like inside what exactly inside the box. So basically this specific level, it compares what is inside the box and what is coming from the text. So it describes over the text so that nothing important is missed. These are the candidate box shown in the, just we see like in red on the bottom, right here. So generate candidates box, every detected object is represented by its bounding box, as we see like x1 and also y1, x2, y2. So these boxes are passed forward for high-level reasoning. And then the key idea is the stage defines everything that might matter. The next stage decides what actually matters in this scenario. And then we have this part, ROIA, line extract local visualization features. And for each candidate box, it extracts the visual pixels inside the box, converts them into the feature map, splits them into multiple regions, and these tokens represent color, shape, texture, local context inside the box. So that gives the LLM a finely detailed view of each object, not just a single average vector. And we also have, as we see, a high-level comprehension, so the very top part. This is where the big brain reasoning happens. So LLM becomes the decision maker. And projection into the language, all the visual features, global plus regional, and are transformed into the embeddings. that the LLM can understand. So the reason we do this because LLMs think in word space, not pixel space. So in projection, it converts visual info into something like a visual word, so the LLMs can understand. So this is basically about their architecture, and then in short and simple. So finds everything relevant even if the meaning is unclear. So high-level LLM use reasoning and language understanding to choose the correct regions, or say this specific object you're asking for, it does not exist in the image. So these are the two-stage system, involves multi-object detection, negative descriptions, complex language semantics, and rejecting non-existing objects. So all of which older LLMs would fail. And this slide shows how ROD MLLM unifies referring, grounding, and object detection using the LLMs itself, and a little bit what happened in mathematics. So the LLM reads the description wrapped in P, just like we do like in an HTML form. So and then it sees anchor tokens like an AO or A1 that points into specific image region. If then checks each region and decides which ones match the descriptions. If nothing matches, it confidently outputs none, which older LLMs would not do this. And then we also have an anchor tokens, also let the LLM talk about or describe the exact region, which is how we unify all these tasks under a single framework. So this is how this allows the system to use the LLM's own reasoning to score detection, keeping everything unified and consistent. All right, so now let's talk about how whole system works by combining low-level acquisition with the high level. All right, so this small figure, like the one up here, as we see, organize the visual information before the LLM starts reasoning. And then the core idea is that the input to the LLM has multiple level visual tokens. So first, we have the image tokens, the one we have see like on the right side, and this come from the visual encoder and represented the entire image at global level. So there are N tokens, and then text image token, so of these every scenario. So next, for every detected region, the system creates region tokens. Each region is represented not by like one token, but by 4 separate tokens. This is what they call it multi-granularity. So these 4 tokens correspond to finer patches inside the region, capturing more detailed information. So, and then we add a region anchor token for each region, like A1, A0 or A1. And these tokens belong to region 0. This belongs to region 1 or 2. So the LLM receives the global image token, the detailed region tokens, and the anchor token. So they link everything together. And also this figure shows how MLMs handles several different tasks using one unified framework, so they can understand about the image and also talk about what part of the image they're talking about. So now let's go and talk about automated data annotations pipelines. So in this slide, we see the goal here is to generate rich natural description and accurate labels without relying on an expensive human annotation. So step 1 is we see object description generation. So the base detection dataset, like in the object 365, it's a huge dataset, normally only gives a very simple label, such as a car or something. So these are too basic for free-form language detection. So the authors use internal VL, 76 billion parameters to turn each object into a full natural language descriptions that includes objects, its action, and its surrounding. So basically we only had an object with name, now we have an object with several info about the specific object. And then this is another part of the building a data set from grounding data set. This is using like grounding data set like FLIRC, 30,000 entities. So these data sets already include captions and bounding boxes, which makes them great starting points. On the left side, we can see that step 1 is generating descriptions for existing objects. Each image in that data set comes with multiple captions and entity level boxes. So this is another part of how to make this. So together, this approach produces data that is far more expensive and realistic than traditional grounding data sets. And it trains the model to handle both accurate matches and tricky mismatch. So, and then we have to talk about a little short and simple about the results. So on the rough COCO benchmarks, we see the main takeaways that MLLM performs much better than any other competitors, as we see like it ended up by 86.7 on this data set, which handles complex descriptions, especially which have the longest sentence, and it also generalized task where the model must also reject non-existing objects. So basically, if you just ask the model like, about the pen, but which basically pen does not exist in that picture, the model should say like it's not in there. So basically, the model should say no because of non-existing data. And in other data sets, we have even like comparing those 3-4 different, and in any case, it's coming with the higher score. This slide we have compared, like we're comparing the model performance compared to other models. In the first row, the description asks for 2 donuts, as we see like other models, like the OVID and everything, like just basically in this picture, it's showing up, it's detecting all these donuts, but in our case, we have correct, accurate data, what we just asked for. Or basically hot air balloon landing on the ground, which is like they're just flying in the sky, like all those models are detecting whatever it is, just because of the air balloon is mentioned in text. But in our case, no one is detected, nothing is detected, just because of everything is in the air. So exactly the same scenario applied for these 2 different cases. So this is pretty much about those, how we can just combine computer vision with NLP and then understand and detect an object that we exactly would want from the image. If our object name is not mentioned, or maybe object is not shown in the image, model says, nope, this object you're asking for is not mentioned or it doesn't exist in the image. So basically, this is all about